We introduce enabling learning-based navigation and obscurance with lightweight, low-cost millimeter wave radar using cross-model contrastive learning of representations. This work is carried out by the team NCTU for the DARPA Subterranean Challenge. Navigating and avoiding obstacles in unknown environments are essential capabilities for mobile robots. For advice conditions such as rainy, foggy, or smoke-filled environments, commonly used sensors for navigation such as LiDAR and camera are impaired by those obscurance. In contrast, millimeter wave can penetrate through smokes and measure the distances of surrounding objects, for example, in search and rescue missions. Our work focuses on single-chip millimeter wave radars, which have caught a lot of attention due to their lightweight, low cost, and low power consumption for indoor applications. However, the range data measured by single-chip millimeter wave radars is noisy and sparse, making indoor navigation with such millimeter wave radars challenging. To address these challenges, we proposed a cross-model contrastive learning method to navigate the robot through smoke using only single-chip millimeter wave radar. Range inputs from 4 low-cost millimeter wave modules with a total 240-degree field of view are used in an end-to-end reinforcement learning to generate robot actions. We started with training an agent running infinite navigation in a simulator using deep reinforcement learning algorithms. The trained control policy network can be divided into a feature extraction encoder and a decision-making network. To directly use the noisy and sparse raw millimeter wave radar data to control the robot, we trained a new millimeter wave data encoder using the contrastive learning framework. The basic idea is to maximize the agreement between millimeter wave inputs and LiDAR inputs in the training stage. The millimeter wave data encoder is expected to generate representations that are similar to LiDAR representations, but without actual LiDAR inputs. During the inference phase, we use only millimeter wave radar data as input and generate representations for the decision-making network. For comparison, we also trained a generative reconstruction model that can generate LiDAR-alike range data used in a pipeline of 2 separate networks. One is the network of generative reconstruction, and the other is a network of control policy trained in the simulator to navigate the robot. Here are some demos of our proposed methods. We evaluate our robot navigation performance in a smoke-filled maze built with cardboards. To evaluate the robustness of the millimeter wave radar. High concentration smoke was emitted at 3 places in the maze. We also evaluate our robot navigating in a general indoor environment at another building using contrastive learning approach. The robot can safely navigate through the corridor and the door. Please find more details in our paper. This work is supported by various funding agencies. We greatly appreciate the support. Thanks for watching.